Chapter 11. Asynchronous Programming. Who can wait quietly while the mud settles? Who can remain still until the moment of action? Lao Tzu, Tao Te Ching. The central part of a computer, the part that carries out the individual steps and makes up our programs, is called the processor. The programs we have seen so far will keep the processor busy until they have finished their work. The speed at which something like a loop that manipulates numbers can be executed depends pretty much entirely on the speed of the computer's processor and memory. But many programs interact with things outside of the processor. For example, they may communicate over a network computer or request data from the hard disk, which is a lot slower than getting it from memory. When such a thing is happening, it would be a shame to let the processor sit idle. There might be some other work it could do in the meantime. In part, this is handled by your operating system, which will switch the processor between multiple running programs, but that doesn't help when we want a single program to be able to make progress while it's waiting for a network request. Asynchronicity. In a synchronous programming model, things happen one at a time. When you call a function that performs a long-running action, it returns only when the action has finished, and it can return the result. This stops your program for the time the action takes. An asynchronous model allows multiple things to happen at the same time. When you start an action, your program continues to run. When the action finishes, the program is informed and gets access to the result, for example, the data read from the disk. We can compare synchronous and asynchronous programming using a small example, a program that makes two requests over the network and then combines the results. In a synchronous environment, where the request function returns only after it has done its work, the easiest way to perform this task is to make the requests one after the other. This has the drawback that the second request will be started only when the first has finished. The total time taken will be at least the sum of the two response times. The solution to this problem in a synchronous system is to start additional threads of control. A thread is another running program whose execution may be interleaved with other programs by the operating system. Since most modern computers contain multiple processors, multiple threads may even run at the same time on different processors. A second thread could start the second request, and then both threads wait for the results to come back, after which they resynchronize to combine their results. In the following diagram, the thick lines represent the time the program spends running normally, and the thin line represents time spent waiting for the network. In the synchronous model, the time taken by the network is part of the timeline for a given thread of control. In the asynchronous model, starting a network action allows the program to continue running while the network communication happens alongside it, notifying the program when it was finished. Another way to describe the difference is that waiting for actions to finish is implicit in the synchronous model, while it is explicit under our control in the asynchronous one. Asynchronicity cuts both ways. It makes expressing programs that do not fit the straight line model of control easier, but it can also make expressing programs that do follow a straight line more awkward. We'll see some ways to reduce this awkwardness later in the chapter. Both prominent JavaScript programming platforms, browsers and Node.js, make operations that might take a while asynchronous rather than relying on threads. Since programming with threads is notoriously hard, understanding what a program does is much more difficult when it is doing multiple things at once. This is generally considered a good thing. Callbacks. One approach to asynchronous programming is to make functions that need to wait for something take an extra argument, a callback function. The asynchronous function starts a process, sets things up so that the callback function is called when the process finishes and then returns. As an example, the setTimeout function, available both in Node.js and in browsers, waits a given number of milliseconds and then calls a function. Waiting is not generally important work, but it can be very useful when you need to arrange for something to happen at a certain time or check whether some action is taking longer than expected. Another example of a common asynchronous operation is reading a file from a device's storage. Imagine you have a function readTextFile that reads a file's contents as a string and passes it to a callback function. The readTextFile function is not part of standard JavaScript. We will see how to read files in the browser and in Node.js later in chapters. Performing multiple asynchronous actions in a row using callbacks means that you have to keep passing new functions to handle the continuation of the computation after the actions. An asynchronous function that compares two files and produces a boolean indicating whether their content is the same might look like this. This style of programming is workable, but the indentation level increases with each asynchronous action because you end up in another function. Doing more complicated things, such as wrapping asynchronous actions in a loop, can get awkward. In a way, asynchronicity is contagious. Any function that calls a function that works asynchronously must be asynchronous. using a callback or similar mechanism to deliver its result. Calling a callback is somewhat more involved and error-prone than simply returning a value, so needing to structure large parts of your program that way is not great. Promises. A slightly different way to build an asynchronous program is to have asynchronous function return an object that represents its future result instead of passing around callback functions. This way, such functions actually return something meaningful, and the shape of the program more closely resembles that of a synchronous program. This is what the standard class promise is for. A promise is a receipt representing a value that may not be available yet. It provides a then method that allows you to register a function that should be called when the action for which it is waiting finishes. When the promise is resolved, meaning its value becomes available, such functions, there can be multiple, are called with the result value. It is possible to call then on a promise that is already resolved. Your function will still be called. The easiest way to create a promise is by calling promise.resolve. This function ensures that the value you give it is wrapped in a promise. If it's already a promise, it is simply returned. Otherwise, you get a new promise that immediately resolves with your value as its result. To create a promise that does not immediately resolve, you can use promise as a constructor. It has a somewhat odd interface. The constructor expects a function as its argument, which it immediately calls, passing it a function that it can use to resolve the promise. For example, this is how you would create a promise-based interface in the read text file function. Note how, in contrast to callback style functions, this asynchronous function returns a meaningful value, a promise to give you the contents of the file at some point in the future. A useful thing about the then method is that itself returns another promise. This one resolves to the value returned by the callback function, or if that returned value is a promise, to the value that the promise resolves to. Thus, you can chain multiple calls to then together to set up a sequence of asynchronous actions. This function, which reads a file full of file names and returns the content of a random file in that list, shows this kind of asynchronous promise pipeline. The function returns the result of this chain of then calls. The initial promise fetches the list of files as a string. The first then call transforms that string into an array of lines, producing a new promise. The second then call picks up a random line from that, producing a third promise that yields a single file name. The final then call reads this file, so the result of that function as a whole is a promise that returns the contents of a random file. In this code, the function used in the first two then calls returns a regular value that will immediately be passed in the promise returned by then when the function returns. The last then call returns a promise text file name, making it an actual asynchronous step. It would also have been possible to perform all these steps inside a single then callback, since only the last step is actually asynchronous. But the kind of then wrappers that only do some synchronous data transformations are often useful, such as when you want to return a promise that produces a processed version of some asynchronous result. Generally, it is useful to think of a promise as a device that lets code ignore the question of when a value is going to arrive. A normal value has to actually exist before we can reference it. A promise value is a value that might already be there or might appear at some point in the future. Computations defined in terms of promises by writing them together with then calls are executed asynchronously as their inputs become available. Failure. Regular JavaScript computations can fail by throwing an exception. Asynchronous computations often need something like that. A network request may fail, a file may not exist, or some code that is part of the asynchronous computation may throw an exception. One of the most pressing problems with the callback style of asynchronous programming is that it makes it extremely difficult to ensure failures are properly reported to the callbacks. A common convention is to use the first argument of the callback to indicate that the action failed, and the second to pass the value produced by the action when it was successful. Such callback functions must always check whether they received an exception and make sure that any problems they cause, including exceptions thrown by functions they call, are caught and given to the right function. Promises make this easier. They can be either resolved, the action finished successfully, or rejected, it failed. Resolve handlers, as registered with then, are called only when the action is successful, and rejections are propagated to the new promise returned by then. When a handler throws an exception, this automatically causes the promise produced by its then call to be rejected. If any element in the chain of asynchronous action fails, the outcome of the whole chain is marked as rejected, and no success handlers are called beyond the point where it failed. Much like resolving a promise provides a value, rejecting one also provides a value, usually called the reason of the rejection. When an exception in a handler function causes the rejection, the exception value is used as the reason. Similarly, when a handler returns a promise that is rejected, that rejection flows into the next promise. There's a promise.reject function that creates a new immediately rejected promise. To explicitly handle such rejections, promises have a catch method that registers a handler to be called when the promise is rejected, similar to how then handlers handle normal resolution. It's also very much like then in that it returns a new promise, which resolves to the original promise's value when that resolves normally and to the result of the catch handler otherwise. If a catch handler throws an error, the new promise is also rejected. As a shorthand, it then also accepts a rejection handler as a second argument, so you can install both types of handlers in a single method call. Then accept handler, reject handler. A function passed to the promise constructor receives a second argument alongside the resolve function, which it can use to reject the new promise. When our read text file function encounters a problem, it passes the error to its callback function as a second argument. Our text file wrapper should actually check that argument so that a failure causes the promise it returns to be rejected. The chains of promise values created by calls to then and catch thus form a pipeline through which asynchronous values or failures move. Since such chains are created by registering handlers, each link has a success handler or a rejection handler or both associated with it. Handlers that don't match the type of outcome, success or failure, are ignored. Handlers that do match are called and their outcome determines what kind of value comes next. Success when they return a non-promise value, rejection when they throw an exception, and the outcome of the promise when they return a promise. The first then handler function isn't called because at that point of the pipeline the promise holds a rejection. The catch handler handles the rejection and returns a value, which is given to the second then handler function. Much like an uncalled exception is handled by the environment, JavaScript environments can detect when a promise rejection isn't handled and will report this as an error. Carla. It's a sunny day in Berlin. The runway of the old decommissioned airport is teeming with cyclists and inline skaters. In the grass near a garbage container, a flock of crows noisily mills about, trying to convince a group of tourists to part with their sandwiches. One of the crows stands out, a large scruffy female with a few white feathers in her right wing. She is baiting people with a skill and confidence to suggest she's been doing this for a long time. When an elderly man is distracted by the antics of another crow, she casually swoops in, snatches his half-eaten bun from his hand, and sails away. Contrary to the rest of the group, who look like they're happy to spend the day goofing around here, the large crow looks purposeful. Carrying her loot, she flies straight towards the roof of a hangar building, disappears into an air vent. Inside the building, you can hear an odd tapping sound, soft but persistent. It comes from a narrow space under the roof of an unfinished stairwell. The crow is sitting there surrounded by her stolen snacks, half a dozen smartphones, several of which are turned on, and a mess of cables. She rapidly taps the screen of one of the phones with her beak. Words are appearing on it. If you didn't know better, you'd think she was typing. This crow is known to her peers as call crow, but since those sounds are poorly suited for human vocal cords, we'll refer to her as Carla. Carla is a somewhat peculiar crow. In her youth, she was fascinated by human language, eavesdropping on people until she had a good grasp of what they were saying. Later in life, her interest shifted to human technology, and she started stealing phones to study them. Her current project is learning to program. The text she is typing in her hidden lab is in fact a piece of asynchronous JavaScript code. Breaking in. Carla loves the internet. Annoyingly, the phone she is working on is about to run out of prepaid data. The building has a wireless network, but it requires a code to access. Fortunately, the wireless routers in the building are 20 years old and poorly secured. Doing some research, Carla finds out that the network authentication mechanism has a flaw she can use. When joining the network, a device must send along the correct 6-digit passcode. The access point will reply with a success or failure message depending upon whether the right code is provided. However, when sending a partial code, say only 3 digits, the response is different based on whether those digits are the correct start of the code or not. Sending incorrect numbers immediately returns a failure message. When sending the correct ones, the access point waits for more digits. This makes it possible to greatly speed up the guessing of the number. Carla can find the first digit by trying each number in turn until she finds one that doesn't immediately return failure. Having 1 digit, she can find the second digit in the same way and so on until she knows the entire passcode. Assume Carla has a join Wi-Fi function. Given the network name and the passcode as a string, the function tries to join the network, returning a promise that resolves if successful and rejects if the authentication failed. The first thing she needs is a way to wrap a promise so that it automatically rejects after it has taken too much time, to allow the program to quickly move on if the access point doesn't respond. This makes use of the fact that a promise can be resolved or rejected only once. If the promise given as its argument resolves or rejects first, that result will be the result of the promise returned by with timeout. If, on the other hand, the set timeout fires first, rejecting the promise, any further resolve or reject calls are ignored. To find the whole passcode, the program needs to repeatedly look for the next digit by trying each digit. If authentication succeeds, we know we have found what we're looking for. If it immediately fails, we know the digit was wrong and must try the next digit. If the request times out, we have found another correct digit and must continue by adding another digit. Because you cannot wait for a promise inside a for loop, Carla uses a recursive function to drive this process. On each call, the function gets the code as we know it so far, as well as the next digit to try. Depending upon what happens, it may return a finished code or call through to itself to either start cracking the next position in the code or try again with another digit. The access point tends to respond to bad authentication requests in about 20 milliseconds, so to be safe, this function waits for 50 milliseconds before timing out a request. Carla tilts her head and sighs. This would have been more satisfying if the code had been a bit harder to guess. Async functions. Even with promises, this kind of asynchronous code is annoying to write. Promises often need to be tied together in verbose, arbitrary-looking ways to create an asynchronous loop. Carla was forced to introduce a recursive function. The thing the cracking function actually does is completely linear. It always waits for the previous action to complete before starting the next one. In a synchronous programming model, it'll be more straightforward to express. The good news is that JavaScript allows you to write pseudo-synchronous code to describe asynchronous computation. An async function implicitly returns a promise and can, in its body, await other promises in a way that looks synchronous. We can rewrite crack passcode like this. This version more clearly shows the double loop structure of the function. The inner loop tries digits 0 to 9 and the outer loop adds digits to the passcode. An async function is marked by the word async before the function keyword. Methods can also be made async by writing async before their name. When such a function or method is called, it returns a promise. As soon as the function returns something, that promise is resolved. If the body throws an exception, the promise is rejected. Inside an async function, the word await can be put in front of an expression to wait for a promise to resolve and only then continue the execution of the function. If the promise rejects, an exception is raised at the point of the await. Such a function no longer runs from start to completion in one go like a regular JavaScript function. Instead, it can be frozen at any point that has an await and can be resumed at a later time. For most asynchronous code, this notation is more convenient than directly using promises. You do still need an understanding of promises, since in many cases you'll still interact with them directly. But when wiring them together, async functions are generally more pleasant to write than chains of then calls. Generators. This ability of functions to be paused and then resumed again is not exclusive to async functions. JavaScript has a feature called generator functions. These are similar but without the promises. When you define a function with function asterisk, placing the asterisk after the word function, it becomes a generator. When you call a generator, it returns an iterator, which we already saw in Chapter 6. Initially, when you call powers, the function is frozen at its start. Every time you call next on the iterator, the function runs until it has a yield expression, which pauses it and causes the yielded value to become the next value produced by the iterator. When the function returns, the one in the example never does, the iterator is done. Writing iterators is often much easier when you use generator functions. The iterator for the group class from the exercise in Chapter 6 can be written with this generator. There is no longer a need to create an object to hold the iteration state. Generators automatically save their local state every time they yield. Such yield expressions may occur only directly in the generator function itself and not in the inner function you define inside of it. The state a generator saves when yielding is only its local environment and the position where it yielded. An async function is a special type of generator. It produces a promise when called, which is resolved when it returns finishes and rejected when it throws an exception. Whenever it yields awaits a promise, the result of that promise, value or thrown exception, is the result of the await expression. A corvid art project. One morning, Carla wakes up to an unfamiliar noise from the tarmac outside of her hangar. Hopping onto the edge of the roof, she sees the humans are setting up for something. There's a lot of electric cabling, a stage, and some kind of big black wall being built up. Being a curious crow, Carla takes a closer look at the wall. It appears to consist of a number of large glass-fronted devices wired up to the cables. On the back, the devices say LEDTech SIG 5030. A quick internet search turns up her user manual for those devices. They appear to be traffic signs with a programmable matrix of amber LED lights. The intent of the humans is probably to display some type of information on them during their event. Interestingly, the screens can be programmed over a wireless network. Could it be they are connected to the building's local network? Each device on a network gets an IP address, which other devices can use to send it messages. We talk more about that in Chapter 13. Carla notices that her own phones all get addresses like 10.0.0.20 or 10.0.0.33. It might be worth trying to send messages to all such addresses and see if any one of them responds to the interface described in the manual for the signs. Chapter 18 shows how to make real requests on real networks. In this chapter, we'll use a simplified dummy function called request for network communication. This function makes two arguments, a network address and a message, which may be anything that can be sent in as JSON, and returns a promise that either resolves to a response from the machine at a given address or rejects if there was a problem. According to the manual, you can change what is displayed on a SIG 5030 sign by sending it a message with content like command display data 0003, where data holds one number per LED dot, providing its brightness 0 means off, 3 means maximum brightness. Each sign is 50 lights wide and 30 lights high, so an update command should send 1500 numbers. This code sends a display update message to all addresses on the local network to see what sticks. Each of the numbers is an IP address that can go from 0 to 255. In the data it sends, it activates a number of lights corresponding to the network's last address number. Since most of these addresses won't exist or will not accept such messages, the catch call makes sure network errors don't crash the program. The requests are all set out immediately, without waiting for other requests to finish, in order not to waste time when some of the machines don't answer. Having fired off her network scan, Carla heads back outside to see the result. To her delight, all the screens are now showing a stripe of light in their upper left corners. They are on the local network and they do accept commands. She quickly notes the numbers shown on each screen. There are 9 screens arranged 3 high and 3 wide. They have the following network addresses. Now this opens up possibilities for all types of shenanigans. She could show crows rule, humans drool on the wall in giant letters, but that feels a bit crude. Instead, she plans to show a video of a flying crow covering all of the screens at night. Carla finds a fitting video clip in which 1.5 seconds of footage can be repeated to create a looping video showing a crow's wing beat. To fit the 9 screens, each of which shows 50 by 30 pixels, Carla cuts and resizes the videos to get a series of 150 by 90 images, 10 per second. Those are then each cut into 9 rectangles and processed so that the dark spots of the video, where the crow is, show a bright light, and the light spots, no crow, are left dark, which should create the effect of an amber crow flying against a black background. She has set up the clip images variable to hold an array of frames, where each frame is represented with an array of 9 sets of pixels, one for each screen, in the format that the sign expects. To display a single frame of the video, Carla needs to send a request to all the screens at once, but she also needs to wait for the results of these requests, both in order not to start sending the next frame before the current one has been properly sent, and in order to notice when the requests are failing. Promise has a static method all that can be used to convert an array of promises into a single promise that resolves to an array of results. This provides a convenient way to have some asynchronous actions happen alongside each other, wait for them all to finish, and then do something with the result, or at least wait to make sure they don't fail. This maps over the images in frame, which is an array of display data arrays, to create an array of request promises. It then returns a promise that combines all of these. In order to be able to stop playing a video, the process is wrapped in a class. This class has asynchronous play methods that return a promise that resolves only when the playback is stopped again via the stop method. The wait function wraps set timeout in a promise that resolves after the given number of milliseconds. This is useful for controlling the speed of the playback. For the entire week that the screen wall stands, every evening when it is dark, a huge glowing orange bird mysteriously appears on it. The event loop. An asynchronous program starts by running its main script, which will often set up callbacks to be called later. That main script, as well as the callbacks, run to completion in one piece uninterrupted, but between them the program may sit idle waiting for something to happen. So callbacks are not directly called by the code that scheduled them. If I call setTimeout from within a function, that function will return by the time the callback function is called, and when the callback returns, control does not go back to the function that scheduled it. Asynchronous behavior happens on its own empty functions call stack. This is one of the reasons that without promises, managing exceptions across asynchronous code is so hard. Since each callback starts with a mostly empty stack, your catch handlers won't be on the stack when they throw an exception. No matter how closely together events such as timeouts or incoming requests happen, a JavaScript environment will run only one program at a time. You can think of this as running a big loop around your program called the event loop. When there's nothing to be done, that loop is paused, but as events come in, they are added to the queue and their code is executed one after the other. Because no two things run at the same time, slow-running code can delay the handling of other events. This example sets a timeout that dallies until the timeout's intended point of time, causing the timeout to be late. Promises always resolve or reject as a new event. Even if a promise is already resolved, waiting for it will cause your callback to run after the current script finishes rather than right away. In later chapters, we'll see other types of events that run on loop. Asynchronous bugs. When your program runs synchronously in a single go, there are no state changes happening except those that the program itself makes. For asynchronous programs, this is different. They may have gaps in their execution during which other code can run. Let's look at an example. This is a function that tries to report the size of each file in an array of files, making sure to read them all at the same time rather than in sequence. The async file name part shows how arrow functions can also be made async by putting the word async in front of them. The code doesn't immediately look suspicious. It maps the async arrow function over the array of names, creating an array of promises, and then uses promise.all to wait for all these promises before returning the list they build up. But this program is entirely broken. It'll always return only a single line of output listing the file that took the longest to read. Can you work out why? The problem lies in the plus equals operator, which takes the current value of a list at the time the statement starts executing, and then the await finishes sets the list binding to be that of the value plus the added string. But between the time the statement starts executing and the time it finishes, there's an asynchronous gap. The map expression runs before anything has been added to the list, so each of the plus equals operators starts from an empty string and ends up, when its storage retrieval finishes, setting a list to the result of adding its line to the empty string. This could have easily been avoided by returning the lines from the mapped promises and calling join on the result of promise.all, instead of building up the list by changing a binding. As usual, computing new values is less error-prone than changing existing values. Mistakes like this are easy to make, especially when using await, and you should be aware when the gaps in your code occur. An advantage of JavaScript's explicit asynchronicity, whether through callbacks, promises, or await, is that spotting these gaps is relatively easy. Summary. Asynchronous programming makes it possible to express waiting for long-running actions without freezing the whole program. JavaScript environments typically implement this style of programming using callbacks, functions that are called when the action is complete. An event loop schedules such callbacks to be called when appropriate, one after the other, so the execution does not overlap. Programming asynchronously is made easier by promises, objects that represent actions that might complete in the future, and async functions which allow you to write an asynchronous program as if it were synchronous. Exercises. Quiet times. There's a security camera near Carla's lab that is activated by motion sensor. It's connected to the network and it starts sending out a video stream when it is active. Because she'd rather not be discovered, Carla has set up the system that notices this kind of wireless network traffic and turns on a light in her lair whenever there's activity outside so she knows when to keep quiet. She's also been logging the times at which the camera is tripped for a while and wants to use this information to visualize which times in an average week tend to be quiet and which tend to be busy. The log is stored in files holding one timestamp number as returned by date.now per line. The camera logs.txt file holds a list of log files. Write an asynchronous function, activity table day, that for a given day of the week returns an array of 24 numbers, one for each hour of the day, that hold the number of camera network traffic observations seen in that hour of the day. Days are identified by numbers using the system used by date.getDay, where Sunday is 0 and Saturday is 6. The activity graph function provided by the sandbox summarizes such a table into a string. To read the files, use the text file function defined earlier. Given a file name, it returns a promise that resolves to the file's content. Remember that new date timestamp creates a date object for that time, which has a getDay and getHours methods returning the days of the week and the hours of the day. Both types of file, the list of log files and the log files themselves, have each pieces of data on its own line, separated by new line characters. Real promises. Rewrite the function from the previous exercise without async wait using plain promise methods. In this style, using promise.all will be more convenient than trying to model a loop over the log files. In the async function, just using await in a loop is simpler. If reading a file takes some time, which of these two approaches will take the least time to run? If one of the files listed by the file has a typo and reading it fails, how does that failure end up in the promise object that your function returns? Building promise.all. As we saw, given an array of promises, promise.all returns a promise that waits for all the promises in the array to finish. It then succeeds, yielding an array of result values. If a promise in the array fails, the promise returned by all fails too, passing on to the failure reasons for the failing promise. Implement something like this as a regular function called promise_all. Remember that after a promise has succeeded or failed, it can't succeed or fail again, and further calls to the function that resolve it are ignored. This can simplify the way you handle a failure in your promise.